All right, let's try some example problems, some practice problems with Gibbs free energy. So starting here, the reaction above is carried out at 25 degrees Celsius in 1 atmosphere. We want to calculate the delta H, delta S, and delta G for using the following data. So I have these substances. I've got my delta H of formation values, my S standard values, my entropies. And I want to calculate delta S, delta G, and delta H. Well, to start with, I could calculate delta F, or delta H, using my delta HF values. Remember that delta H of reaction, my enthalpy of the reaction, is going to be equal to the products minus the reactants. Enthalpy of products minus reactants. So I'm going to start with my products, 2SO3. So I have 2 times for SO3, delta H of formation is negative 396. Minus the products, minus the reactants, products minus reactants. And my reactants are 2SO2 and oxygen. Well, oxygen is 0, so I could actually leave that factor out. So 2SO2 is going to be 2 times negative 297. And just to be really thorough here, I'm going to go ahead and show why my oxygen is not a factor. I need to just add in the 0, which we know is not going to change our value there. When you plug that in your calculator, 2 times negative 396 minus 2 times negative 297, I end up with negative 198. And that is enthalpy in kilojoules per mole. So that's kilojoules per mole of reaction. Okay. That's delta H. Let's look at delta S. So if I wanted to calculate it, I'm going to do the same process. Delta S can be calculated by using your entropy values of the products minus the entropy values of the reactants. So I'm going to have 2 times, for the product, I've got SO3, 2 times 257. Minus, and then our reactant side, 2SO2, 2 times 248, plus, and don't forget to put this all in brackets because we want to do the total of the products minus the total of the reactants. All right, and then for oxygen, it's going to be 205. All right, and that will tell us our entropy. Change in entropy is negative 187. And that's joules per Kelvin, right? Joules per Kelvin mole of reaction, we could say. So looking at these values, I want to try to make sense of it, make sure that we can make sense of it in general. Delta H is negative. That means this is an exothermic reaction. Well, it's a combustion reaction, so that kind of makes sense that it would be an exothermic reaction. And then I see that delta S is negative, so our entropy actually decreases in the process. Let's see if that makes sense. I've got 2 SO2 and I've got 1 O2. That means I've got 3 moles of gas on the reactant side, and I have 2 moles of gas on the product side. So the randomness is decreasing a little bit. And that's what this shows us, is the randomness decreased a little bit. Now, be careful. I have joules per Kelvin mole. I want to convert that to kilojoules per Kelvin mole. So this is a good place for us to go ahead and do a little bit of dimensional analysis. Insert an equation here. We're going to multiply by a fraction. Remember that there are 1,000 1,000 joules in a kilojoule. So 1 kilojoule, 1,000 joules. And then we can figure out, I'm going to take my negative 187 and multiply by 1 over 1,000. So that ends up being negative 0.187 kilojoules per Kelvin mole. And that allows us to do our calculation for delta G. Remember, delta G, there's a few different ways to find it, but I want you to think about the one that involves enthalpy and entropy, since we have those two values. This is really good practice with this equation. Delta G equals delta H minus T delta S. Delta G equals delta H, so that's this value, minus, and then our temperature is 25 degrees Celsius, which if you add 273, we've got to turn that into Kelvin. Okay, so actually let's do that down here. T equals 25 degrees Celsius plus 273 equals 298 Kelvin. So that's what we're going to be using there. So we end up with delta G equals delta H minus T delta S minus that temperature multiplied by the delta S value that we just found up here, which is negative 0.187 kilojoules per Kelvin mole. And remember, we converted to kilojoules because we have to have the same units to get a good answer. Then we could put this in our calculator. Just plug and chug negative 198 minus, start your parentheses, 298 times 0.187, end up with a negative 253 kilojoules per mole of reaction. Okay, so that's a good practice with a few different things. Using your enthalpy and entropy of formation to figure out the delta H and delta S, and then using those values to get delta G. I think this might make a really good FRQ, just kind of a hint for you guys. This is probably something you need to be able to do because it's multiple steps. You get a point for this and you get another point for doing this. You maybe get a point for knowing that you got to convert to Kelvin and doing that right, and then you get another point for putting it all together and ending up with the correct delta G. So be thinking about that type of thing when you go through these practice problems.